Good afternoon all. Today the topic will be antiviral agent. I'll be taking the revision for antiviral agents. So let's start with the introduction. Start with the introduction of antiviral agents. So what are antiviral agents? So viruses are non-cellular infectious agents which take over the host to survive and multiply. That means they don't have their own mechanism to multiply. To depend upon the host for their multiplication and their survival. So these are viruses. They can infect humans, plants, animals, and even the bacterial cells. More than 400 different types capable to infect. So there are almost around 400 species that can be, and recent one is your coronavirus, okay, which affects your lungs. They're responsible for influenza, chickenpox, measles, mumps, viral pneumonia, rubella, smallpox, and many other viral infections. They're involved with many of the diseases. And if not detected, they take over our entire immune system. Okay, so they are more deadly diseases. Virus, and some of the examples, if we can say AIDS, which is one of the most causative agents of virus. Virus can be transmitted to humans by a variety of means: through air, by infected hosts, through sneezing, and coughing, as you have been looking at in case of COVID-19, through arthropods or ticks like yellow fever and cholera tick fevers, through insect bites, tick bites, through physical contact. Some of these viruses which cannot survive outside the host, such as HIV, cold sore, genital herpes, rabies. So they are spread through physical contact. Foodborne, waterborne, like hepatitis A, E, and viral gastroenteritis. So these are some of the causative way through which the viral infections are transmitted to humans: through your air, when you're coughing, through insect bites, through physical contact, or through food and waterborne infections, where these viruses are predominantly present. Okay. So, what are the classifications of viruses? There are two types of viruses. One is DNA virus. Example is adenoviruses that cause acute respiratory tract diseases, herpes simplex, chickenpox, varicella zoster virus. These are the examples of DNA virus. They contain a DNA subunit in it. RNA viruses, example, it are the causative agent of encephalitis, retroviruses, the examples of this thing. Respiratory illness, influenza, diarrhea, AIDS. These are all the examples of retroviruses, means these contain DNA as their, RNA as their basic unit, a cellular unit. Okay, now let's go for the basic structures of the structure. So they can be classified as DNA virus, which may either contain a single stranded DNA or a double stranded DNA. RNA virus, similar, they have a single stranded RNA, but sometimes they might contain a double stranded RNA. The nucleic acid is protected within a plasma protein. If you see the structure next to that, so it is entire all this RNA and DNA, they are surrounded by the protein material, and they itself is protected by a protein coat that is known as capsid. If you can see small beads, they are the capsid. They prevent that is a protein coat which protects your nucleic acid within your viruses or the virus liver cell. The capsid contains your nucleic acid, and it is called nucleocapsid. The whole structure of your virus is known as vira. The form of the virus takes place when it is outside the host cell. Okay, the entire structure of the virus is known as vira. Okay, so this is the basic structure of your virus. So now, how does this viruses attack our body? So this is an example of HIV virus, which I'm showing it on the screen. So first of all, this viruses have got a particular sites in which it binds. So the GP120 glycoprotein on the surface of the virus, this glycoprotein 120, which is present on the site of the virus, they bind to the specific CD4 cells on the receptor. Okay, on the which attaches to the CD4 receptors. Once they get attached to the particular receptor in the cell, so once they get, the next stage the viral contents, so they get enter into the human cells. Okay, through endocytosis, the cell wall breaks. Once it get attached to this particular receptor, it breaks the cell wall, and all the contents from your virus enters into your human cells. So once they enter, so they contain enzymes called reverse transcriptase catalase. This is an enzyme which is the first step for the synthesis of your DNA copy or the RNA. So if it contains a DNA, it will synthesize a copy of this particular DNA or the particular viral RNA. Okay, and the synthesis of second DNA complementary strand to the first one will be synthesis. So this is the first step, that is enzyme reverse transcriptase, which will prevent this DNA synthesis, where the DNA double-stranded DNA will be synthesized. Once this DNA is synthesized within the outside the in the cell by using the reverse transcriptase, then they enter this double-stranded DNA, then enters the host cells. Then the enters the host cells, and they get incorporated into your DNA strands, and they use the mechanism, and they will multiply over time, and they will liberate your RNA, which will then come out of the this leads to transcription. That is the fifth step that you can see in the slide. Fifth step is transcription of results in the transcriptions of the DNA results in the production of RNA. So your DNA splits up, it leads to formation of RNA. This RNA serves as a genome for new virus. So it will synthesize all the proteins. It will synthesize the proteins. It will synthesize the required proteins which is necessary for formation of your formation of your virus, to produce a new virus. So it will synthesize all the proteins which is necessary for formation of your new virus. So once all the new viruses are formed, when all the units required for the viruses are formed here, then they engulf themselves. They engulf them through the process of budding. So it will create an entire surrounding around them. All these proteins will get accumulated to it, and it will form the required viral structure. And once the entire viral structure is formed through, and it comes out. So the next step is the complete viral HIV particles are assembled together. So what all things I said? Your proteins are synthesized. What all proteins are synthesized? So all the proteins that are necessary for your DNA, for your virus formations are accumulated. They are assembled. And in macrophages, the HIV buds out of the cell without rupturing the cell, and the T cells. The HIV exits the cell by rupturing and effectively killing the cell. So once it happens, the entire cell gets destroyed and it comes out of the host cell after it. So CD4 is your cell where the viruses bind in case of it. So this is the life cycle of your HIV virus. This is the life cycle of your HIV virus. Okay. So this was the brief thing of how the viruses attack the human. How the viruses attack, they then break up in the cells, they get introduced into the cell, that will produce its new that will produce the new protein materials, DNA, which then gets introduced into, which will then gets introduced into the nucleus of this in the cell, and the nucleus gets introduced into host DNA. Then it synthesizes the respective RNAs, which produces the required proteins for your virus function. And then through your macrophages, HIV bud comes out of the body and it infects the cells. Okay, so this is how the viruses. So this is the basic thing about your viral multiplication. How does it act? So let's go how the antiviral drugs act. The antiviral agents either block the viral, so the binding, so there's the point of attachment of the viral is blocked. That is the first method. Or it prevents the exit from the cells. So either it will prevent the entry or exit from them. And the most prominent place where the antiviral agents act is your hosts, where they multiply inside the host cells, where they use the different host cell mechanism for the because they are dependent upon the host. So the most active place where the antiviral agents act is your replicating phase of your viruses. The earlier the treatment is given, the better is the result. So in case of viral treatment, so as you see even in now in the coronavirus, the better you see the symptoms, if you treat it at that moment, the spreading of the infection can be controlled. Similarly in case of other viruses. So that's why, so as soon as if you show some symptoms, you should get treated and that can be cured. The better, the faster you get the treatment, the better you can arrest the replication of your viruses and inhibit the capability to reproduce. Okay, the viruses obligate intracellular microorganisms, so they are present in the body of our cell. They are present within the body, and the drug targets viral process must also penetrate into. So if you see, all the antiviral agents should act inside the host cells, so it might destroy the host cells also. Okay, therefore the drugs that cause a negative impact on the virus also likely to have negative impact on the normal pathway of the host cells, because they affect the normal host cell, because once the virus enters, then only the antiviral agents mostly act, so it can destroy your host cell also. This is why this is the negative part of your antiviral, because they affect even the normal host cells. This is how the antiviral agents act. So how does the antiviral agent, as it is a continuation. So as I explained when I was teaching you how the HIV virus. So what is the first step? What is the first step? Attachment of the virus. Attachment of the virus to the receptor on the host cell. The first step is attachment of your virus to the receptors on the host cell surface. Then entry of the virus through the host cell membrane. So once they get attached, then they split up, and through the site of attachment, then of the cell membrane and uncoating of your viral nucleic acid. So once it gets attached, so it will segregate at the host cell membrane, and synthesis of regulatory protein, nucleic acid and polymerases occur. So all the regulatory proteins required for first is your DNA synthesis, and all the and once the DNA enters in the host cell, it will through the enzyme polymerase, nucleic acid polymerase, it will synthesize your new RNA and DNA, and which will then synthesize your structural protein. That is synthesis of late and structural protein. So once your DNA and RNA is, so your other materials which is necessary for your coating of your viruses, they can be produced using your host cell mechanism. And once all the necessary structures are produced, they assemble into a mature viral particle, and once the mature, then they will bud off from your cyst cell, and antiviral agent can, and in all the steps that I've mentioned, the antiviral agents can potentially target in these steps. So they can potentially target the viruses in all the mentioned 8 steps. Okay, they can attack. So this is the life cycle of your virus. So what is the first step? That is, the virus gets absorbed on the cellular membrane, then they penetrate. Second step is they penetrate into your cytoplasmic membrane. Then next step is uncoating of your viral plasmid. Then all the viral DNA enters into your nucleus. So it will form your new DNA. Then it gets introduced into your DNA of your normal cell and synthesis of an earlier mRNA. And this mRNA results in your early translation into your required proteins, which is necessary for your formation of your viral DNA. And all these required proteins are then synthesized. So that is your early translation, and then DNA synthesis and late transcription. And during the late transcription synthesis of your proteins, that is capsid proteins are synthesized. So it will form the outer coating of the and coming together. So once this capsid and all is formed, all the materials which are present different, they come together, form a capsid. And once everything gets assembled of frequent multiplication, these viruses are again. So this is the basic life cycle of your virus. So you have to know the basic life cycle of your virus, how the viruses enter, uncoating, early transcription, DNA synthesis, late transcription where it synthesis, where the mRNA synthesizes the required proteins for your capsid formation, then the assembly of all the required proteins that takes place, then they bud off from then the release of your virus from the cells. That is the, okay. So now comes the classification of anti. So there is according to the diseases in which they act. So this is one of the classification. Okay, what is the first classification according to the diseases which they act? The first class is anti-herpes virus agents. The example is Azaclavir, Famiclovir, Ganciclovir, Valaciclovir, Idoxuridine, and Foxcarbonate. Okay, this acts on herpes. The second class is antiretrovirals. So there are some examples, that is nucleotide reverse transcriptase inhibitor. So in exam they write the drugs which act on reverse transcriptase inhibitors. Okay, give an examples of reverse transcriptase inhibitor with the mechanism of action. This was the question that was asked. Example, if it is a nucleoside, a reverse transcriptase inhibitor, then example is lamivudine, tenofovir, zidovudine, zaclitopin. Next, non-nucleoside reverse transcriptase enzyme. So non-nucleotide means they don't have structure similar to your nucleotides or your nitrogen bases which are present in your DNA. So examples are nevirapine and delaveridine. Okay. Next example is protease inhibitor. These are the drugs which inhibit your protease inhibitors, which initiates your protein synthesis in your mRNA transcription. Example is ritonavir, indinavir, etc. Anti-influenza drugs like amantadine, rimantadine, okay. Next class of drug is non-selective. Examples interferon and also sumaverin. So these are some of the examples, classifications of your antiviral. Next is your chemical classification. Chemical classification is purine nucleoside and nucleotide antagonist. So they are antagonist of your purine. So next is your pyrimidine nucleotide or nucleoside antagonist. Example is Idoxuridine. Non-nucleoside antagonist is, as I mentioned earlier, that is delaveridine, nevirapine, and all. Thiosemic carbazine example, Methisazone. Fourth class is adamantane amine, that is adamantane. Next class is interferons, and miscellaneous drugs are SURAMIN. So these are some of the examples of your chemical classification of your antiviral agents. Now let's go for individual. So these are the sites. This is in this particular site. This shows where this particular drug acts. So as I explained, first is point of attachment and entry of the. So which are the drugs which act? That is Virazole. So these are antibodies, and Docosonar. So these are the antibody treatment. Next is they prevent the uncoating. So the drugs that prevent the uncoating of your viruses are adamantine, rimantadine. That's used in the treatment of influenza. The drug that prevents the penetration of your this thing are interferons, alpha interferons. Okay. So, and the next is nucleic acid synthesis. They block by mostly the examples are cyclovir, entecavir. These are the drugs which inhibit the nucleic acid synthesis. Next drug is the drugs which prevents the protein synthesis and crossing. So these are protease inhibitor. Okay, and blockage of your release of this enzyme. So example is means the drug which inhibits the release of the virus. So the examples are neuraminidase inhibitor. Okay, they inhibit the release of the drug from the viruses from the cell. So now first class is nucleoside analogs. So nucleoside analogs. So these are nothing but they have the structure similar to your nucleosides. What are the nucleosides? Purine, that is adenine, guanine, cytosine, thymine, and uracil. So these are all the different nucleosides which are present in our. So these compounds, they are analogous to, and they just act as an antimetabolite or an antagonist to this particular. They have close structural, as explained in this slide, they have got close structural similarities with the natural metabolites like your purines and pyrimidine. They are designed via structural modification of this natural metabolite. So what are these natural nucleosides? Adenosine, that is your guanine attached to your guanidine, adenine, uracil, which is attached to a ribose sugar and phosphate. So they are the structural modification of this compound. They interfere with the normal metabolic process and inhibit the enzymes involved in this process. So as I mentioned when I was teaching anti-cancer, so they act as an antimetabolite and prevent the enzymes which are involved in this synthesis. They are usually considered as a product because they are activated in vivo. So once they enter the body, they have to be converted into an active. As such, they are inactive, but once they enter into the body, they get transformed into its active form. So they should be first phosphorylated inside the infected cell, and then the mechanism of your viral DNA synthesis is inhibited by inhibiting the enzyme DNA polymerase or by getting incorporated into the DNA chain. So either they will block the enzyme DNA polymerase or they get introduced itself into your DNA chain and impairing the DNA chain elongation process and thus prevent the protein synthesis and thus cause the. They are chemically either purine or pyrimidine analogs. So these are the basic thing about nucleoside analog. Okay. Now the first example is a cyclovir. The first example is a cyclovir. The first example is so it is an analog of what? It's an analog of your guanine. So it's an analog of your guanine. It is an example of deoxyguanosine. It is an example of deoxyguanosine. So what is guanosine? It is nothing but an purine antagonist. The basic unit is your guanine. So guanine unit contains an 2-amino 6-oxopurine ring, which is attached to your deoxyribose sugar. You can see in the right hand side, it is connected to a deoxyribose sugar. The structure of acyclovir is similar to that of your deoxyguanosine, where your guanine unit is linked to your ribose sugar. Where your guanine unit is linked to your ribose sugar. If you can see O, it is an methoxy-ethoxy group, which is, if you can see, it is containing an methoxy ethanol linkage. If you see your guanine is linked to an methoxy ethanol linkage. So this is the structure of your cycle. So what are the three major way of action? They can inhibit your DNA polymerase enzyme. They inhibit your tubulin polymerization, which is necessary for your DNA during your DNA formation or new cell formation. Okay, these are the various, or they get incorporated into your DNA change and thus preventing the. So this is how the acyclovir acts. Let's go deep into it, further into your mechanism of action of your acyclovir. So if you can see, what is your acyclovir? It's a 3-step phosphorylation process. So first step is it gets converted into monophosphate by your virus specified thymidine kinase. It is selective activation. So it requires thymidine kinase, that is herp virus specific thymidine kinase. This is known as herp virus specific thymidine kinase. So this is the particular enzyme which is only present in your viruses, not in your human. So this is a specific kinase enzyme which phosphorylates your acyclovir into acyclovir monophosphate. Then the di and triphosphate compounds by the host enzyme. So this particular, then once it comes, it gets converted into your, and this in presence of your herpes virus DNA polymerase enzyme. This acyclovir triphosphate get incorporated into your viral DNA, and the viral DNA synthesis is inhibited. Thus the acyclovir. So they inhibit your viral DNA polymerase, thus inhibiting the viral DNA polymerase with binding of your DNA templates as a reversible complex. So once this gets introduced into your DNA polymerase, it will form an irreversible complex, and this inactivates the particular. And incorporation, second is incorporation into your DNA, viral DNA, and thus terminating the chain elongation process. This is how the acyclovir acts. This is the mechanism of action of your acyclovir. Now this is very important. Now this thing is very important. Why? Acyclovir shows selective toxicity towards the virus, not the host. So acyclovir does not inhibit DNA polymerase in your normal uninfected cells. So they not. Why acyclovir does not inhibit the normal DNA in the normal uninfected? Because the first step is polymer requires the viral version of your kinase and 100 times more active than the host M. So first step of this, it is done by your viral kinase, which is not by your host. So why? Because this particular enzyme is 100 times more potent, effective than your normal host enzyme. And there is a selective uptake of by the infected. And also there is one more thing, is that this particular acyclovir, it's selectively taken up by the infected cell. And acyclovir triphosphate is 15 times more selective on viral DNA park as compared to that of cellular polymerase. So because of this specific reason, acyclovir shows selective toxicity towards the viral cell as compared to that of your normal host cell. That's why it is most preferred drug in the treatment of antiviral agents. Okay. So some of the side effects: nausea, vomiting, diarrhea, headache, drowsiness, and confusion, and used in herpes simplex virus type 1, type 2, varicella zoster virus, and different types of infections. Okay, so this has got a wide variety of uses. Some of the analogs of acyclovir are ganciclovir, famiclovir, peniciclovir. So these are some of the examples. If you see the structure, it is almost the same. Only that difference that you can see, it is on the side chain. It is on the side chain. So this was only done in the introduction of your extra OH group and all, or your acetate. So this, in case of famiclovir, it acts as a prodrug because this particular diacetate ester gets converted into your ganciclovir. Okay, sorry, it converted into your gets converted in your peniclovir. So this is a prodrug of your, this famiclovir is a prodrug, acetate prodrug of your peniclovir. If you see, there is no O in that, and it has got a diol over there, which increases its water solubility and improves the oral viability. So these are the analogs of your cyclovir or your purine antagonist. Okay. The next drug is Ribavirin. So this is a synthetically modified drug which has got a modified base. If you see, it contains a tetrazole amide. It contains a 1,2,4 triazole, and it contains an amide which mimics to that of your, this particular stuff is an biester of your purine metabolite. Of your purine metabolite, and it contains a ribose sugar which is attached to it, which contains a ribose sugar attached to it. It is a broad spectrum antibiotic. So it is basically an 1,2,4 triazole with an amide linkage, which acts similar to that of your purine base. Okay, basically it is used as an aerosol in the treatment of influenza A, B, and C. That's basically, it is used for the treatment of retrovirus. It is used for the treatment of retrovirus, as in case of RNA virus. Okay, herbs and measles. So this is Ribavirin. So if you see the Ribavirin, it is nothing but an triazole, 1,2,4 triazole with an amide linkage, and the nitrogen at the first position is attached to your ribose sugar. It is attached to a ribose sugar. Okay, so this is the structure of your Ribavirin. Okay, so what is the mechanism of action of your Ribavirin? So Ribavirin in your viral, by using viral and cellular kinase, gets converted into monophosphate. Okay, by kinase enzymes, which phosphorylates your Ribavirin to your Ribavirin monophosphate. This Ribavirin monophosphate inhibits iosine monophosphate dehydrogenase. So this particular prodrug, so when it gets converted into Ribavirin monophosphate, this inhibits the dehydrogenase, which is necessary for conversion of your inosine monophosphate to your xanthine monophosphate, and which is necessary for the synthesis of guanosine triphosphate synthesis, which is one of the nucleotide. Moreover, Ribavirin monophosphate gets converted into triphosphate, which inhibits your RNA polymerase, viral RNA polymerase. This is how they inhibit. Either they get introduced into your this thing, or they inhibit your enzyme called inosine monophosphate dehydrogenase, which is necessary for conversion to your guanosine triphosphate. So your guanosine triphosphate is not synthesized, so this will inhibit your DNA synthesis. This will inhibit your DNA synthesis. This is inhibit your DNA synthesis particular, and the other is it will inhibit your RNA polymerase enzymes. This is how the two drug, this is how the drug Ribavirin acts. Okay, so next example is trifluridine. Next example is trifluridine. So what you see it in this structure, particular structure. So this is an example of pyrimidine analog. This is an pyrimidine antagonist. This is an example of an pyrimidine antagonist. And so So it is, if you see, it contains basically a uracil linkage. If it contains a uracil linkage with the carbonyl group at the second and the fourth position, and thus contains a CF3 group, and it contains a CF3 group at the fifth position. So, and the first position nitrogen is attached to your deoxyribose sugar. It is attached to a deoxyribose sugar. If you see the structure properly, it is basically a pyrimidine analog, and basically it contains, and it is an analog of your thymidine, okay, or your, it's a trifluoromethyl uracil or a trifluorothymidine. Okay, so tri is and only active against your DNA such as HERT virus. So it is used in the treatment of adenoviruses. It is used for the treatment of your adenovirus, and it is, as you say, it is similar to your thymidine analog. Means in case of thymidine, it contains a CF3 at CH3 in the third position, in the fifth position, whereas in case of trifluoridine, it contains a CF3 at the fifth position. It is used as an 1% sterile solution for alternative treatment of keratoconjunctivitis caused by herp simplex virus. Caused by herp simplex virus. Mechanism of action similarly, it gets converted into monophosphate, trifluoride, monophosphate, and other two triphosphate, which inhibits your viral DNA polymerase, inhibiting your DNA synthesis by producing false DNA, and this leads to breakage and miscoding error in your RNA and protein synthesis. This is the mechanism of actions. If you see, the mechanism of actions are same for most of the drug, but only in case this is specific for your DNA viruses. This is only specific for the DNA viruses. Okay, so this is about trifluoride. Now go for zitopirine. The structure is asked in the exam. The structure is asked in the exam, okay, with the mechanism of action. With the mechanism of action. With the mechanism of action. So what you see, it is similar to your thymidine analog. It is a 3-azido, because in this case, if you see the exam, in the previous example, there was a CF3 at the fifth position. Here it contains CS3, and it contains a deoxy sugar. So if you can see, it contains a deoxy. I've kept the cursor over there. It contains a deoxy sugar and one of the hydroxyl group. And one of the hydroxyl group in your deoxyribose sugar is replaced by an azido, that is N3 group. So one of your OH group is replaced by an azido group. If you can see the previous structure, that's trifluoridine, it contains an OH at 1, 2, 3 position, whereas in this case it contains an azido group at the 3 position. It is usually active against the retrovirus. It is active against your retrovirus. So what is the mechanism of action? What is the mechanism of action? Similar to that of, so in presence of thymidine kinase, it gets monophosphated, then through other thymidine kinases, it gets converted to your triphosphate. Your fifth position OH gets converted to your triphosphate. So this acts as an target for your enzyme DNA polymerase. Okay, and this inhibits your reverse transcriptase enzyme. So this inhibits your, it acts as a competitive inhibitor of normal nucleoside triphosphate or the enzyme reverse transcriptase, which is necessary for your DNA synthesis. And they inhibit your enzyme called reverse transcriptase, thus inhibiting your DNA synthesis and RNA synthesis, which is your initially after your it gets uncoated. This reverse transcriptase is necessary for formation of your DNA, respective DNA strand. So this is inhibited by your zidovudine, also known as azidothymidine or retrovir. So other name of zidovudine is retrovir azidothymidine. D. Okay, this is of it, and it is very important from your examination point of view, where the structure is been repetitively asked in your the structure and the inhibit the enzyme reverse transcriptase, which is necessary for your enzyme for your DNA synthesis, for replication of your formation of your new DNA. Okay. Next example is idoxuridine. If you see the structure of idoxuridine, it is similar to that of trifluridine. Only thing is that your CF3 is replaced by your iodo group. Your CF3 is replaced by your iodo group. Rest all things are same. Rest all things are same. It is an antagonist of your antimetabolite of your thymidine, and it is an example of pyrimidine antimetabolite used as an antivirus. Similar to that, same thing, the mechanism of action is same. It gets incorporated, forming faulty DNA which breaks down easily, and synthesis of wrong viral protein. And also, they once it gets triphosphorate forms triphosphate, it inhibits your DNA polymerase enzymes, okay, and thus inhibiting your DNA synthesis. This is the mechanism of action of idoxuridine. So idoxuridine is nothing but your ido at the fifth position, similar to that of your trifluridine. Trifluridine contains CF3 at the fifth position, whereas in case of idoxuridine, it contains an ido at the fifth position with the pyridine linkage, with the pyrimidine linkage, okay, and oxo at the second and the fourth position. So it is an thymidine anti-metabolite. So, okay, if you see the structure on the right, it is thymidine. So it is similar to that of your thymidine. Only your CS3 of your thymidine is replaced by your iodine. That's why it is called iroxuridine. So mechanism of action similar. It gets converted first. Iodine first phosphorylated by host cell to an active triphosphate, and this phosphorylated drug is incorporated into a viral nucleic acid synthesis by false pairing system that replaces a thymidine, results in your chain termination. So instead of thymine getting introduced, your idoxuridine gets incorporated in a DNA sequence, and thus it causes your chain termination. It causes your chain. So, but it is toxic. That's why it is basically used. It's not used for your systemic use, but only for topical application. Idoxuridine is used only for topical. So the main active form is your triphospho form. So it gets activated only when it gets converted into your triphosphate form, that is by the enzyme thymidine kinase, which is present in your host cell. That's why they act as a true drug. That's why they act as a true drug. These are some of the examples of your nucleoside analog that interfere with your DNA and RNA synthesis. That is cytarbine. So cytarbine is nothing but your cytosine analog. It is an cytosine analog. It is an cytosine analog, which is an pyrimidine containing an NH2 at the fourth position, and a ribose sugar, which is attached to a ribose sugar. Next example is Virazole. It is nothing but an adenine analog. It is nothing but an adenine analog. It is used for the treatment of insects. We have to know what is adenine and guanine, everything. Okay, it is an nucleoside which contains an ribose sugar attached to it. Next example, other examples are idoxuridine, then acyclovir and ribavirin. An example is ribavirin. These are the example of antiviral. Please recollect the structures. So acyclovir is an example of your guanine antagonist. Guanine, and whereas vitarmin is an example for adenosine antagonists. So remember these examples according to the nucleic nitrogen bases in your DNA. Now next example is non-nucleoside reverse transcriptase enzyme inhibitor. The next examples are these are examples of non-nucleoside reverse transcriptase inhibitor. They are used for the treatment of HIV and AIDS. They are used for the treatment of HIV and AIDS. So, mechanism of action, they bind directly to the HIV1 reverse transcriptase enzyme, resulting in your inhibition of DNA and RNA dependent polymerase activity. So, once these enzymes get inhibited, your DNA and RNA polymerase activity, it's inhibited. So, inhibiting your protein synthesis. So, and the binding site for non-nucleoside reverse enzyme is near but distinct from that of your nucleotide reverse transcriptase inhibitors. Okay, so this is the structure. If you see the structure of your, this thing, so it is nothing but a bipyrido which is connected, linked to a which is near diazepine. So if you can see that, I'll be just showing you the structure. You can look at the board. You can see the board. Just tell me if you can see the. So it is nothing but a pyridine ring which is connected to a diazine. You got 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, 7. Azapine. Okay, diazepine. So your first nitrogen next is connected to an cyclopropyl ring with an amide at the top, and next to it, it is also connected to an 4-methyl pyridine moiety. It is connected to an 4-methyl pyridine moiety. So this is the structure of Nevirapine. Apine means 7-membered ring connecting to a 2-pyridine. Okay, so this is Nevirapine. So it is an example of non-nucleoside reverse transcriptase inhibitor. Okay, the adverse effects are mild to moderate rashes, toxic epidermal necrolysis, hypersensitivity, severe or life-threatening liver toxicity. So it leads to liver toxicity. It leads to liver toxicity. Okay, so please remember the structure of this drug. It is as a diazepine ring moiety which is linked to 2-pyridine moiety. So one of these unsubstituted, and other one contains a 4-methylated pyridine, which contains an cyclopropyl linked to your first nitrogen of azepine and contains an amide link which is attached to your 2-pyridine moiety. So this is the structure of Nevirapine. So it's very easy to remember. 2 fused. It's a bipyridofused diazepine which contains which is methyl connected to an cyclopropyl and an amidic. Okay, so now let's go for the next example. So next example is delaviridine. Okay, delaviridine. So what is the structure of delaviridine? So if you can see, you can bifurcate the structures into 3 different moieties. So first thing, it contains an amino. So 1, 2, 3, 4, 5. So 4-methyl sulfonate methyl sulfonate group of your indole. So first is it contains an indole group which is methyl sulfonated through an amine substitution at the 5th position. 1, 2, 3, 4, 5. So this is your methyl sulfonated indole group which is connected to an piperazine. So it is a saturated ring diazine containing a which is connected to your indole by a carbonyl group which is connected to your indole ring by a carbonyl. So if you can look at the board, everybody, can you see the board? So first ring is your indole, that is indole ring, which contains 1, 2, 3, 4, 5, which is connected to an methyl sulfonate and methyl sulfonate at the 5th position. Okay, now this is connected by at the second position by a carbonyl group to your piperazine. Okay, to your piperazine, and this piperazine, particular piperazine ring is connected to your pyridine ring, connected to your pyridine ring, which contains an isopropyl group at the third position. An isopropyl group at the third position. So this is the structure of your delaviritine. So what all things you are doing? It contains an indole moiety, which is connected to a piperazine moiety by a carbonyl group, and the piperazine moiety is connected to a pyridine group, which contains an at the second position, and which contains an isopropyl group at the third position, and your indole ring contains an methyl sulfonate group at the fifth position. So this is the structure of your delaviritine. This is the structure for your delaviritine, and it is an example for your non-nucleoside reverse transcriptase inhibitor. This is an example for your non-nucleoside reverse transcriptase inhibitor. It prevents the replication of HIV. So if you want to give an example for anti-HIV drugs, so these are the example. Questions are asked in the exam for 2 months, specifically for the treatment of anti-HIV drugs. So mechanism of action, similarly, it binds directly to the reverse transcriptase of your HIV-1 virus and blocks your DNA-RNA dependence polymerase and DNA polymerase active, DNA and RNA dependent DNA polymerase active. Delivery is basically used for the treatment of HIV infection or in combination with other retroviral agents. Some side effects are mild headache, fatigue, allergic reaction, chills, edema, and joint pain. So these are some of the side effects of this drug. So please remember the structures of this drug. It's simple. You have to remember 3 parts. One is your indole heterocycle connected by a carbonyl to your piperazine, which is 1,4-diazine, saturated diazine, and which is connected at the second position of your pyridine, which contains an isopropyl group attached at the third position, and the indole group contains methyl sulfonate group at the fifth, amino methyl sulfonated group at the fifth position. So this is the structure of delivery. So please remember the structures. These questions can come for 2 months in your exams to write the structures. Next is adamantane. So next class of drug is adamantane. So it is an example of tricyclic amide. So it is nothing but 3 cyclohexyl rings. So you have to just draw 3 interconnected cyclohexyl rings. So if you can see the structure on the board. Okay, so first draw 1 cyclohexyl ring, then draw the second both form of your cyclohexyl ring, then connect the first and the second through a CH2 linkage, and at the point of contact it contains an amino group. That is adamantine, amine or adamantine. All this adamantine, everything, the name is same. Okay. So did you understand the structure? Is simple. Draw a cyclohexyl ring. Then at the down portion, it is connected by an similar to your chair form of your cyclohexane, and the central carbon is attached to another central carbon of it by a CH2 link. So that forms 3 cyclic cyclohexane ring, which is and the point of attachment, it contains an amino group, that is your adamantine or adamantane. So they are tricyclic. They are used for the prevention and treatment of influenza caused by influenza A virus. So how do they act? They appear to involve by inhibition of uncoating of your RNA virus, thereby blocking the transfer of viral RNA into the host. So if your uncoating is prevented, so your viral RNA cannot enter into your host cell, and this is your first step, that is inhibition of your entry of your viruses into your host cell, and thus involve in prevention of penetration of your intact virus into your host cell. So it prevents the entry only of your viruses into your host cell. So this is the mechanism of action of adamantine or adamantane. Okay. Now next is an example of thiosemicarbazole derivative. Thiosemicarbazole. What is thiosemicarbazole? It is nothing but, so if you can see on the top of the word, if you can see the top of the word, it contains NH2C double bond S NHN. So this NH2C double bond S NHNH. So this particular linkage is known as thiosemicarbazole linkage. Okay, it is known as thiosemicarbazole link, which is connected to a dioxoindane. Okay, so it is connected to a dioxoindane. So just if you can see the structure on the board, if you see the structure on the board, you can see the structure on the board. So first is that you should draw a saturated ring. You can draw a indole ring. You can draw a indole. First draw a indole. Just draw a indole. So this is your indole, which is, so second position it contains a carbon. Even third carbon, there is a indenone. It is called as indenone. Okay, it contains a 2 carbonyl at a second end. This is then connected to your NHC double bond S NH2. This is nothing but your Methisazone. Okay, it is nothing but your Methisazone, which is used as an antiviral. So it is used as, so this particular moiety that is known as statin, which contains an indole ring, which contains an dioxo, that is carbonyl group at the second and the third position. It is known as your statin. So if it contains an methyl, it is known as, if this contains an methyl over there, it is known as Methisazone, and if it contains an ethyl, it is known as Ethizazone. If it contains an ethyl group, it is known as Ethizazone, according to the substitution at the nitrogen. So if the nitrogen is methylated, it is known as Methisazone. So what is the mechanism? How it does act? It acts by interfering with the translation of your mRNA message into your protein synthesis on the cell microsomes. So it prevents your protein synthesis. So your mRNA, which binds to your ribosomes. So this will interfere with the translation of your mRNA message into your protein synthesis on the cell ribosome, producing a defect in proteins incorporation into it. So it will prevent the protein formation. So once all your DNA, RNA, which is synthesized inside the cell, so once they come out, this messenger RNA, they have to bind to the ribosomes for your protein synthesis, So this will inhibit this particular process, and this is basically used as a prophylactic agent against smallpox infection. So it is basically used as an prophylactic agent against smallpox viruses. Okay, this is the mechanism of action. And the last drug is SURAMIN. So what is this SURAMIN? The structure looks very big. It's not that difficult to remember. Basically, it is this SURAMIN is used for the treatment of African sleepiness or your river blindness. Basically, it is used for the treatment of various tryposomal infection, basically known as African sleepiness or river blindness. It is basically, and it's also used for the treatment of sleeping sickness without central nervous system involvement. So it is also used for in the treatment of your sleeping. But why it is used in your as an antiviral? So if you go to the mechanism of action, SURAMIN works by blocking various growth processes within the parasite. So they will act at various growth processes. Means growth process means all the required necessary ingredients in the body is necessary for your parasite. It is inhibited. So what does this drug do? It blocks the insulin growth, NADH oxidation enzymes. So they block various enzymes which are necessary in your growth function, and this limits the cell production and migration. So it prevents your cell production as well as migration. And that, when this happens, the parasite becomes immobile and eventually, so all the necessary enzymes and metabolic process, if it is blocked by this particular compound, so that is your SURAMIN. So there, this will destroy the energy requirement of your cell, as well as it will inhibit the, this will inhibit the migration of, make it immobile and migration, and it, which will eventually lead to it. So what is the structure of your SURAMIN? So what is the structure of your SURAMIN? How do you recollect the structure? So if you see the structure, it can be divided into two equal halves. It can be divided into two mirror image of each other. So what do you see in the first, you look at the right hand side. So it contains an naphthalene ring. It contains a naphthalene ring. What it contains? It contains a naphthalene ring and a sulfonate group, sulfonic acid group at 1, 3 and 5 position. So if you contain, it contains a sulfonic acid at 1, 3 and 5, and it contains an amino group at the 8th position. So this is the basic ring. First you draw this structure. That is a, first you draw an naphthalene containing an sulfonic acid group at the 1st, 3rd and 5th position. Then next thing, it contains an amino group at the 8th. Now this amino group forms a, this forms a benzamide group. Okay, so it forms an amide bond with a 4-methyl 3-amino benzoic acid. So it forms an amide bond with 4-methyl 3-amino benzoic acid. So consider this. What does it form? It forms an amide bond with an 4-methyl 3-amino benzoic. Okay, this is the second part of the structure, attachment in the structure. Third is this, but all this ring amine will form again the amide bond with 3-amino benzoic. It forms an amide bond with, this amino groups forms an amide bond with 3-amino or meta-amino benzoic acid. So this is the one structure. Now this is linked to another part by an carbonyl group, that is an urea linkage to a same similar structure, which is, that is, this amine group then forms an amide bond with your, this amino group forms an amide bond with your 4-methyl 2-amino benzoic acid, again which forms an amide bond with your 1,3,5 trisulfonic naphthalene. So this is the structure of SURAMIN. So this is just a mirror image of your, which is connected by, the two groups are connected by an carbonyl group, and they are the mirror. And if you draw a straight line from the carbonyl group, they are the mirror images of each other. This is how you remember the structure of SURAMIN. So that completes your antiviral agent, and these are all the various examples of your, these are all the agents of your examples of your nucleoside analogs of your reverse transcriptase, okay, which are used for the treatment of your, as an antiviral agent. So that completes your antiviral agent. That completes your antiviral agents.